Welcome back. Let's now look at the equation z is equal to 4x squared plus y squared. So, how does this quadratic surface look like? Well, once again, in this case, the first thing I'm going to do is look at the yz trace. So the yz trace is the trace in the yz plane, and the equation for that is x is equal to 0. So if I plug in x to be 0, then I get this z is equal to y squared, which is a parabola that opens in the direction of the positive z-axis, and the vertex is at the origin. So that is the trace in the plane x is equal to 0, or in the yz plane, is this parabola right here. So now the question is, what is the trace? Well, there are many other traces that I can look at, but the one that I'm going to look at here are the traces that are in planes parallel to the x-axis. Sorry, parallel to the xy plane. So what's the trace in z is equal to? Remember, z is equal to k. That is a plane that is parallel to the xy plane. This is a horizontal plane. So what's the trace in this plane? Well, you just plug in z to be k, you get 4x squared plus y squared is equal to k. And we see that this is the equation of an ellipse. Now, obviously k has to be non-negative because the left hand side here is non-negative. So when k is negative, there is no trace. That is, this obviously, even by looking at the equation itself, because the right hand side is the sum of two squares, the right hand side is non-negative, so the left hand side has to be non-negative. In other words, the graph must be above the xy plane. So the traces in planes parallel to the xy plane are all ellipses. So notice that when k is 0, though, you get just when k is 0, you just get 1.00, the origin, and then when k is 1, 2, and so on, you get these ellipses. So you could see that when for different values of k, so for different values of k, you get ellipses like this that start at the origin, and then the ellipses get bigger and bigger as you go in the positive z direction. So what we see then is that the graph of this equation is an object like this. Now it extends to infinity in the positive z direction. This is called an elliptic paraboloid, and you might ask, when I looked at the traces, why did I look at only these traces? Well, because those are the traces that gives me the best picture of the surface. So how to choose what traces to look at? Well, it depends on your experience. As you sketch these surfaces more and more, you gain the experience of which traces to be looking at. Okay, so now I want to ask. So you might ask, okay, how do I know that this ellipse here, the trace in z equals to k, intersects the trace in the yz plane here? So the way I know that is the following. So you might ask, so I'm going to take k to be 9. So if I take k to be 9, so then I want to know what is the intersection of the YZ trace and the trace in Z equals to 9. Well, K would be 9, so I'm getting this ellipse here, and so the trace in Z is equal to 9 is the ellipse 4x squared plus y squared is equal to 9, and then if I divide by 9 and rewrite this equation in this way, then I see that two of the vertices of the ellipse would be at the points 0, plus or minus 3, and z equals to, because I'm taking z to be 9, so z is 9, and two of the vertices would be right here and here, would be at the points 0, plus or minus 3, and 9. So these are the vertices, and those vertices of the ellipse, they also lie on this parabola, because when y is plus or minus 3, z is 9. So obviously this point lies on the yz trace, where where x is always 0. So you can see why this guy intersects the yz trace. Now, so we've just found that the graph of this equation is this elliptic paraboloid, and the general version of this equation is z over c is equal to x squared over a squared plus y squared over b squared. So anytime you have an equation of this form, that's going to be an elliptic paraboloid. Now here c could be positive or negative. If c is positive, then you have a paraboloid that opens upward, and if c is negative, then you have a paraboloid that opens downward. Now here's the question: what is the graph of y is equal to 4x squared plus z squared? So notice these two equations here, and basically I have swapped y and z. So what is the graph of this new equation here? Well, that's also going to be an elliptic paraboloid. The only difference is now that this paraboloid is going to be extending along the positive y-axis. So you're going to get a paraboloid in the positive y direction, elliptic paraboloid. Okay, so one more question in this regard is, if I look at the graph of z is equal to 4x squared plus y squared, and then what is the graph of z minus 2 is equal to 4 times x minus 2 squared plus y minus 3 squared. So notice that to go from this equation to this equation, I'm subtracting 2 from z, subtracting 2 from x, and subtracting 3 from y. And the graph of this new equation is in fact basically a translation of this surface, translation where you're translating this guy by 2 units in the positive x direction, by 3 units in the positive y direction, and by 2 units in the positive z direction. So you're translating this so that this point here, the vertex point here, comes to the point 2, 3, and 2. So again, when you looking at this translation, notice that if I have a point on this graph, then I have to add 2 to z, 2 to x, and 3 to y to get a point on this graph. So any point that I have here, I add 2 to x, 3 to y, and 2 to z to get a point here. So you see that why we have this translation. Okay, so that's all I want to say about elliptic paraboloids. Okay, I'll see you in the next video, which would be on hyperboloid of one sheet. See you then.